Okay, all right. Happy Friday. It's week 8 Friday, so just a little bit left. Just a little bit left. Okay. All right, we did k-means clustering on Wednesday, and then you have, k-means clustering in your homework. And then we're gonna look at k-means clustering where we put on a kernel function and I guess it does stuff. All right. So just a review of the k-means clustering algorithm. It's kind of this iterative back and forth algorithm. There's kind of I guess it could be considered a special case of the EM algorithm, but that's next week. But it's basically there's these two stages. One is you calculate centroids, and then the other is you reassign points, right? So you calculate centroids, reassign points, calculate centroids, reassign points, and you just kind of go back and forth until it settles on convergence. There's some issues if you have too many. If you're searching for too many clusters K, it might not converge. Each time you run it, it might converge to different solutions. And even the question of how many clusters K is like an impossibly difficult problem. And again, part of the problem with unsupervised learning is that there's not necessarily a right answer, which just makes things harder. So, but anyway, here's just kind of a little diagram, and then we'll search for 3 clusters. And again, here I'm just starting off with random assignment of points. We could have used a different initialization algorithm and just picked 3 random points and set those as centroids, but here I'll start off with just random assignment of points. And when you do that, these are the 3 kind of centroids that get calculated, and then we reassign points to everything that's the closest. So poor green here, the only points that are closest to green are these 3 points, and lucky for green, it didn't actually get completely eliminated, and something sometimes there's weird little things where it's none of the points get assigned to green, and then it kind of devolves into just searching for 2. But anyway, we do this, and we reassign, recalculate centroids. Now we reassign points, and then a lot more get assigned to green. Recalculate the centroids, and we kind of keep going. And at a certain point, when you reassign the points, nothing gets reassigned, and this is when we'll say it has converged. Okay, so kernelized k-means clustering it's pretty much conceptually, I think it's easy to understand, I think, maybe. But then the implementation looks like magic, because well, anyway, you'll see, okay? So the idea with kernelized k-means is that we apply a kernel function. And so remember, what a kernel function does is it calculates basically what's equivalent to an inner product of your values after they've been transformed, okay? So, we have some function phi that transforms our data. And then after you transform the data, you take an inner product. We saw this when we did SVM. In SVM, we took our data which existed in 2 dimensions. We applied a transformation function that projected the data from 2 dimensions into 3 dimensions, right? So we saw there was that old animation where the points were kind of on the 2D surface, and then they projected it onto kind of what do you call that thing? A paraboloid. And then after they projected it into 3D, we were able to, find a linear plane that separated this, right? So we did that for SVM. And And we're using the same kind of idea of a kernel function where we apply some kind of transformation function, and then we take the inner product. And the kernel function is equivalent to doing this. There's often kind of a shortcut function that doesn't actually require you to do the transformation, which was necessary if we applied something like the Gaussian kernel, because the equivalent transformation for the Gaussian kernel technically transforms it into, infinite dimensional space, right? And then you take the inner product of these infinitely long vectors, and they become, a single scalar value, which seems like a miracle, but I guess it's okay, right? You don't actually have to, your transformation function could be as simple as the identity function, and then, the kernel function here is basically just the inner product, and so, and you just have, XA transpose XB, if you have 2 points XA. Here is another example. So here's a transformation function where we have a coordinate in 2 dimensions, and it transforms it into 3 dimensions. It's a very simple transformation function. It preserves x1 and x2, and it adds a third coordinate, which is x1 squared and x2 squared. The equivalent kernel function can be found by doing, xa dot xb plus the norm of xa squared and norm times the norm of xb squared. And I tried to show this by doing, if I transform xa, I get xa1, xa2, xa1 squared plus xa2 squared, and then here is, dotted with xb1, xb2, xb1 squared, and xb2 squared, right? And then so if you kind of do this, you get xa1, xb1 plus xa2 plus xb2. That's the equivalent of xa dot xb, this part. And then this part over here, xa1 squared plus xa2 squared plus xb1 squared plus xb2 squared. This is the equivalent over here. This is norm of xa squared, and this is norm of xb squared. So, so we can transform it into 3-dimensional coordinates and take the inner product, or the equivalent of the dot product here, or we could just deal with xa and xb directly and not have to. We can skip these intermediate steps and we can go straight from here to here. Okay, which is often what we do for the sake of kind of calculations and stuff. So we don't actually want to do this transformational stuff. Okay. Here's kind of another equivalent thing. So the polynomial kernel takes, you have some constant c plus xa transpose xb raised to the gamma, okay? And if you were to use gamma equal to 2 and set c equal to 0, then you have the equivalent transformation function. There's no easy way for us to figure out transformation functions. These are just kind of like known examples where I know, like, here's our kernel and here's the equivalent transformation function. But for a lot of these things, it's like you've got this kernel function, and theoretically there exists some transformation function that goes from 2D to some higher dimensional space, and then you can do the equivalent inner product. But there's not necessarily like some formula where you go like, oh, okay, if this is the kernel function, this is what our transformation function looks like. I don't know, maybe somebody's figured it out. But this is just another example where I know what the answer is. Okay, so here, if I plug in c equal to 0 and gamma equal to 2, then our result should be xa transpose xb quantity squared. And we can see that's what we would get if I transform xa, or x1 and x2. I'm sorry, this should be xa and xb. I get xa1 squared, xa2 squared, square root 2 of xa1, xa2, and so on and so forth. And you can kind of go through this, and you can see, okay, we're going to get xa1, xb1 squared, xa2, xb2 squared, and then 2 x, this whole mess here, but this is basically the result of, this thing quantity squared. So good old algebra there. Okay. One of the most popular kernels is the Gaussian kernel, which is equivalent to doing this if you have XA and XB. And again, unfortunately, the equivalent transformation function goes into infinite dimensional space based on the Taylor expansion of the exponential function. And I suppose we could find an approximation if we just use like the first 5 terms of the Taylor expansion or something like that. But I haven't bothered trying or something. So that's what we have. And you could read more about these things. And and unfortunately we call these kernel functions, which is just like one of those terms where it just gets reused. Or I mean, not reused. The name kernel just appears in all sorts of different contexts with completely different meanings. So again, we don't even need to think of the transformation itself. And because this kernel is just an inner product for some arbitrary thing, the kernel function can be used kind of as a substitute for any time we see an inner product in the original space. So anytime we see XA transpose XB, we can kind of we can say, what would happen if we had transformed the function and then done the inner product? And then we can just kind of replace XA transpose XB with, the kernel function applied to XA XB. Okay, and that's what we'll try doing here. Let me give you your first view quiz answer. Okay, first one is E. Okay. First one is E. E as an elephant. Okay. All right. So when we actually implement k-means clustering with kernel functions, we're going to do it in such a way that we don't even bother with the 2 steps. So traditional k-means clustering, you calculate centroids, reassign points. Calculate centroids, reassign points. The reassignment of points is based on there's technically like an intermediate step. Calculate centroids, calculate distances to centroids, reassign points based on the distances, right? And so but we said, okay, well, we're going to calculate the distances to the centroids. We got to know where the centroids are. When we use the kernel thing, this kernelized version, we're not going to actually bother calculating the centroids. We're going to just calculate the distance to the centroids. So it seems like magic, but we're going to assign our points, and then we're going to calculate the distances to the centroids, and then reassign points. So, and we're skipping the step of calculating the centroids to begin with, which again, it feels like magic, but we just say, hey, if we know these points belong to this cluster and these points belong to this cluster, can we calculate the distance to the centroid of this cluster and the distance to the centroid of this cluster without actually calculating the centroid of this cluster and without actually calculating the centroid of this cluster? And again, it seems so bizarre, but it can be done. And we'll kind of slightly step through the math that shows this. And it's all based kind of off of, if we know the centroid, this is how we would calculate the distance to the centroid. So if we know the centroid, we would do x minus mu transpose x minus mu, right? So this would be from point N to the centroid of cluster K. And how do we calculate the centroid of cluster K? It's the sum, it's the mean of all of the x values that belong to cluster K, right? So you have some vector Z of zeros and ones that say, does it belong to cluster K or not? And then you take, basically, you add up the points that do belong to it, and you divide by how many points that belong to it. So can we figure this part out without actually figuring out this part, the sum of, not the sum, the figuring out the centroids? Okay, so I'm gonna, yeah, just get excited. All right, so we're gonna basically plug in this thing right here, okay, into in for mu. Okay, so I'm gonna have, so I'm gonna say, all right, we're gonna take the distance from x to the centroid. The centroid is gonna be given by this, and then we have each point to the centroid here. And we have these, when you have kind of the sum of these, you have a whole bunch of different x's. And so we're going to have, we have two letters going on. This is the part that gets a little bit weird and wonky. But, from point N to the centroid, we're going to do this. And so when you kind of take the product of this, this is what we get. Okay, and so I just kind of expand this out, and this part, it feels a little bit weird, but I can combine the sum from m equal to 1 to n and the sum from r equal to 1 to n, because these two things are going to be equivalent, because we're doing the sum of these things. So I can combine them into 2 times this. Okay, but the double sum here, I have to take kind of the product between, 0.1, 0.1, 0.1, 0.2, 0.1, 0.3, so on and so forth. So we have to iterate through all of the r's and iterate through all of the m's. Okay, so this is just kind of, this is what you get when you take the product of these things, right? So it seems like a crazy mess, but I think we can also kind of follow this along up to here. Okay. And so this gives us a formula for calculating the distances to the centroids without having calculated the centroids themselves. Okay, and so this is like if we don't do any kind of transformations. All right, so we can say, all right, let's calculate the distances from each point to the centroid of the clusters. And so we need a vector. It's basically saying these are the points that belong to the cluster, and then and then we take the product between that particular point, and then basically all of the other points, and then the product between all of the points with each other and whatnot. But this will give us the distance from point N to the centroid of cluster K, and we didn't actually need to calculate mu sub K directly. And so this feels like way more work, okay? But when we apply the kernel functions, this actually will save us, because if you have the Gaussian kernel, remember that transformation projects it into infinite dimensional space, and so how do you calculate the coordinate with an infinite dimensional space? You have the centroid has basically a coordinate of infinite length, and so but instead we can kind of use these inner products, and we'll anytime we see an inner product here, so I'm going to go back a couple slides, we can say anytime we see some product xa transpose xb, we can replace it with the kernel function of xa xb. And so that's what I'm going to do. So I'm going to take this thing, which gives us the distances from each point N to the centroid of cluster K, and anytime I see basically an x something transpose x, I'm going to replace it with a kernel function, right? So this is kind of that last line here, and I'm going to just say, all right, let's do kernel of xn. Let's do the kernel between xm and xn. Now let's do the kernel between xm and xr. And and then we have all of these kind of vectors that say, zeros and ones that say, this point belongs to cluster, cluster K, yes or no, 0 or 1. And so we can get the distances from point N to the centroid of cluster K without actually needing to calculate the centroid of cluster K. Okay. Is that all right? Maybe? Okay. So this is how the algorithm works, right? So again, determine how many clusters we're going to search for. I guess part of the initialization is also determine what your kernel function is that you're going to be using. Randomly assign your points to clusters, and then we're going to just repeat this one. It's still iterative, but there's no calculating the centroid. You just reassign values. I guess you calculate distances to the centroids and reassign values, right? Calculate the distances, reassign values. Calculate the distances, reassign values. And you don't actually have to calculate the centroids themselves. You're just calculating the distances directly. Okay, and I mean we could have done this without any transformation using just the linear kernel, I guess, and it would still work. Okay. Okay, so use a very simple data set, and I'm going to do the same thing twice, okay? So I'm going to start off with a two-dimensional data set, and then I'm going to transform it into 3D, and then we'll calculate the centroids in 3D and do k-means clustering in 3D, and we'll find the solution. And then I will do the same thing again, starting off with my same two-dimensional data set, and then we're just going to calculate the distances to the centroids directly without transforming the data, and we'll see we'll get the same results. Okay. Okay, so here is my data, all right, and it's just 0.1, 0.1, and so basically I have 4 points here and then 4 points on the outside, all right? And if I said kind of cluster your points, I think, well, I don't know. I would say, all right, these points are probably similar, and these points on the outside are more similar. And I would kind of cluster them, the inner ring and the outer ring, okay? Now, k-means clustering uses Euclidean distance as a measure of similarity. So k-means clustering would never put this point and this point in the same cluster, because according to Euclidean distance, these two are as different as they can possibly become, right? So traditional k-means clustering, which uses Euclidean distance, would never put the outer points into the same cluster because they're, these opposite corners are about as different as they can be. But we want to try to we're going to use this transformation function. So I'm going to do my transformation into 3D will be x1, x2, and then x1 squared plus x2 squared. So I've got 0.1, 0.1, and then if I do x1 squared and x2 squared, I get 0.02, right? And then 2 squared and 2 squared gives me, 4 and 4 gives me 8. And so when I transform this into 3D, the x1 and x2 coordinates remain the same, and then now I have this additional third coordinate of 0.02s and 8s, okay? And then I randomly assign the points into cluster 1 or cluster 2, and these are my random assignment of who belongs to which cluster. And I'm going to plot them. This is what it looks like. I actually have, there's a little So I think you guys know I do all of my slides in R Markdown, and it's great. But let me run this, run that. Okay, and then see here. okay, here we go. This is what I want. All right, so this over here. So here is, so I'm going to calculate the centroids, and I can actually like rotate this a little bit. And so I think, so this, it's hard to see, but this dot is floating, okay, in the corner of the box. And I think this makes it a little bit easier to illustrate that that dot is floating. So I've got these 5 dots in red and 3 dots in blue. And so the centroid of the 5 dots in red is this dot right here, this bigger dot here, and then the centroid of the 3 dots in blue is, in 3-dimensional space down here. So I don't know if that makes it a little bit easier to see by kind of like rotating it around, okay? So that's what we have there. And so this is the coordinate of our 2 centroids. So centroid A, or cluster A, is in blue, and it's actually, I don't know why. it's hard to manipulate here. Okay, x1 is at negative 0.67 and positive, x2 is at positive 0.67, or I guess this is on y, and then x3 is at 2.68. And then over here for cluster, the red cluster, we're at 0.4, negative 0.4, and then the z coordinate is at 4.8. Okay, so these are the coordinates here. Okay, so again, here it's hard to see when it's just kind of projected down, but this is, I guess this is the perspective that we have in this plot, but it's, I don't know, I think the 3D thing makes it a little bit easier to see. All right, and then so we're gonna we'll calculate the distance to each of these centroids. And, I think we can see that these 4 points will say this centroid in blue is closer, and then these 4 points up here will say the centroid in red is closer. And so at the next iteration, these points up here will get assigned to the red cluster, and the 4 points on the bottom will get assigned to the blue cluster. And so that's what happens. So when we calculate the distances to the blue cluster, centroid A, and we calculate the distances to the red centroid B, and these are the values we get, 7.98, et cetera, and 23.26. And so we get, so these 4 points up here will get assigned to the blue cluster, and then, these are the distances, and we see the distances are smaller for these 4 points to centroid B, so they're going to get assigned to the second cluster in red. And so the resulting plot, this, I don't have the, this is on the surface of the box. Did I plot it? I did. Okay. So after you, something, where did it go? Here we go. No? Okay, well, I didn't create the projection, but this is, imagine the surface of the box up here, and this is in the center of the surface of the box on the top. Okay, maybe that's easier to see. Okay, and then if you recalculate the distances, this is everything is converged here. There's no reassignment, and so we can see, okay, the distances to centroid A at the bottom is very small for these points, and then the distances up here are a lot smaller. Okay, so that's what we have. Okay, so but the slide I want us to pay attention to is this slide, I guess slide 36. These are the distances to the centroids, and we found this by kind of, we did this minus this squared plus this minus this squared, and coordinate 3 minus coordinate, this thing squared, and we calculated the centroids, using Euclidean distance. And what we're going to see is we're going to be able to reproduce the values in these two columns without having to actually calculate the location of the centroids directly, right? Using kind of our formula here, right? So here's our kernel function. The equivalent kernel function for transforming from the two-dimensional coordinate into the three-dimensional coordinate is this thing, xa dot xb, norm of xa squared, norm of xb squared. And then if we use this kernel function, then we can calculate the distances to the centroids directly without actually bothering to calculate the centroids. So I still have a vector, okay, of I have these vectors za and zb, which will just be zeros and ones, okay. It's a 1 if it belongs to cluster 1, and it's a 0 if it doesn't, or cluster A, and it's a 1 if it belongs to cluster 2 or cluster B, and it's a 0 if it doesn't. And we use that in conjunction with our thing, okay? This calculating this thing is actually it's a big to kind of calculate stuff. I'm going to calculate a matrix, kernel matrix of between basically every kind of m and every point 1 through n in m and 1 through n in r. So this is kind of you can imagine the kernel function applied for kind of every coordinate here. And I'm going to use that to get our thing. So this is just a big matrix of basically, what is the kernel function if I apply this and I go for, 1 through n in m and 1 through n in r, right? So we have 8 points, and it kind of calculates all of these things, the kernel values for all possible pairs of points, and this will kind of help us calculate this, right? So I've got all of these kind of nested loops just to kind of show that we've got the double sum. And so I could do the double sum of basically za plus times zm times zr times the kernel function. You could do a little bit of kind of, I guess, trickery and get it this way as well. But you can, just get this double sum value. And then, we calculate all of these things. And basically, so this is, if we're going to go to the first cluster, distances to the centroid of cluster A, if you look at these values, here we found the values. And if I compare this to slide 36, we can see, look at this column, 7.984, 8.251, 7.718. That's the same values, okay? So we're getting the same values just, using this formula, okay? Again, kind of a pain, but it's possible, okay? And nowhere in here do we actually calculate the centroid itself. Same thing with the other column, okay? So if I go back to, I guess, slide 36, so I have 23.265, 23.105. That's what we have, 23.265, 23.105. Yeah. So we get those distances to the centroids, despite not calculating the centroids themselves. So I can kind of just look at these things, and then I can say, okay, between the two values, which one's smaller? And then we're going to say, okay, which one's the minimum? So we'll say column 1, column 2 over here, and those are going to be our assignments. And we would just kind of do these steps of calculating the distances and then reassigning the points. All right. Okay, let me go ahead and give you your second view quiz answer. Or I'll just give you the last two. Second one is C as in cat, C as in cat. And then the third one is B as in bear. Okay. All right, so this is just the code that we've been running. Okay, and then we can just run it again, and then we get we get the same distances that we calculated earlier. Okay, so here's just another example. I'm going to just run the same kind of data here, and I've just made this huge kind of cloud of points. And this is what we have. Okay, what's that?
Oh, like it's polar.
It is polar, yeah. We got cosine and sine, all kinds of good stuff, right? So I have this kind of cluster of points, and then I get this outer ring. And again, if we were to try to do k-means clustering and I just run it, this is the result. It's very unsatisfying because, again, with k-means clustering, it's not going to ever assign points over here into the same cluster as points down here because they're far away. Okay, so what can we do? Well, we can try doing kernelized k-means clustering, right? So we'll apply a kernel function and then do k-means clustering, okay? And so so here I'm going to show the result of clustering, and it's not going to make any sense, the steps in between, because what it's doing is it's going to transform our data from 2D into infinite dimensional space, which we cannot visualize, and then it's doing k-means clustering there, and so there's some imaginary centroid, or not imaginary, there's some centroid that exists in infinite dimensional space, and then we're saying, okay, which centroid is closer, and it assigns the points, and so we get to see which points get assigned to the cluster, but we're only seeing the two-dimensional shadow, okay? So we don't actually get to see what it looks like in this higher dimensional space. So here, so this is just kind of the code, but we're going to use the Gaussian kernel. So this is the a radial basis function kernel. So I've got exp or e to the whatever this is, and I start off with just some random assignment of points, and then it's going to again calculate the distances to the centroids. Okay. And it's equivalent to projecting into higher dimensional space, finding the centroids, and calculating the distances. But we're just going straight to the what is the distances, and then what are the distances, and then reassign the points. So at the next iteration, all right, so this is just kind of the code for calculating the distances, and then distances to the centroid of cluster A and distances to the centroid of cluster B. And then and so after one iteration, these are the assignments, and it's like, okay. But again, so this is just the shadow of what has happened in a higher dimensional space, and we're just seeing the two-dimensional shadow of this. And then we run another iteration, and we say, okay, calculate the distances to the centroids. What's the centroid of red and what's the centroid of black, and calculate the distances there. And now it's kind of assigned the outer ring all to red, and we get kind of like it's almost like a waxing moon or waning crescent moon here. Okay. So this gets assigned, and then that a little bit more gets assigned, and then this finally gets assigned, and then after that there's no changes in assignment, and this is the result. Okay, what's happening? I have no idea. Okay, I have no idea. We just said calculate the distances to the centroids, and it says okay, and it does this. Okay. For the Gaussian kernel, what was the gamma I chose? I just chose a gamma equal to 1. All right. You can play around with this value and pick like a bigger gamma or a lower gamma, and similar to when you did SVM, different values of gamma gave you kind of like different flexibility in terms of the border that that a linear boundary kind of corresponds to. And here it's like, I don't know, like the shape of what it looks like in higher D. But this is what we get. Okay. And so I was just kind of thinking, like, how does this even work, right? This magic of like calculating distances to centroids without calculating the centroids themselves. And I was thinking, like, this is a really silly example, but what if you had to cluster people together, okay? And so I was just thinking of like, okay, what are some celebrities, some actors, and if you were to kind of cluster, can you cluster people together? And I said, okay, I was thinking of like these, Chris Evans and Chris Hemsworth and Jason Momoa, and I would kind of cluster them together. They play these, they're not afraid to, throw a few punches type of characters, right? But also kind of, in these heroic roles or whatever, a lot of times. So, you can kind of cluster these actors together, and then, you have other actors that kind of play a little bit more intellectual roles, or, the way they solve their problems is with their wits and things like that. Maybe a little bit of comedic undertones here as well. And, is there a centroid? I suppose we could imagine, like, what is the average of these these actors, and what is the average of these actors, and what does that person look like? That would be the centroid that, maybe doesn't quite exist, okay? And you could imagine, all right, what if we put in, some additional actor, right? We have, another Chris actor, Chris Pine, who is Captain Kirk, and I don't know whatever he does. And you could say, like, maybe there's some way for us to measure, rather than trying to imagine the centroid, the kind of the average of these three actors and average of these three actors, we can kind of say, okay, well, how similar is this new actor to each of these actors, right? So we're kind of calculating, like, how similar is this one particular actor to the other, we have 6 actors in the data set. And it's kind of like, where's the formula here, right? We're looking at this particular point N, and we're saying, okay, how similar is it to, each of the different actors within our data set? And then by saying, okay, this actor is more similar to these 3 actors than he is to these 3 actors, then we would reassign the point that way, if that kind of makes sense, right? So we're kind of saying, like, okay, how similar are these actors to each other versus like, who's the average of these actors, and then saying, like, okay, how similar are you to the average, right? Because that's what we do in traditional k-means clustering, is we say, okay, what's the average, and then how similar are you to the average? And here we can say, okay, how similar are you to everyone else? We know these ones, these 3 belong to a cluster together, and these 3 belong to a cluster together. And we can say, okay, because you're more similar to, these 3 that are in this cluster, you're going to get clustered with them, and something like that. I don't know if that kind of makes sense in terms of this, like, how are we calculating distances without calculating centroids themselves? So anyway, in the future, I don't know if these these actors are going to become irrelevant, and I'm going to have to find some new set of actors. But I don't know. We all know who these people are, right? Okay, all right. So, although Kumail Nanjiani, he's now a superhero in the MCU as well, right? He's Kingo, I think that's his role. But he also still plays kind of this comedic role in there as well. Okay, that's it for today. Have a great weekend, and Oh, Monday's a holiday, so we'll see you on Wednesday.